think I learned more physics in those 3 days than in any other 3-day interval in my life. After completing an immersion, instructors are eligible to apply to the Jonathan F. Reichert Foundation for a grant to help purchase the lab equipment. I'm grateful for the assistance that the Reichert Foundation provided for my instructional lab. The Emory Physics Department, where I work, covered the rest of the cost. The final catalyst for this book was Emory's Interdisciplinary Exploration and Scholarship Ideas program, which organizes sidecar courses, each of them geared to explore a topic that intersects with and is co-sponsored by 2 existing courses in different departments. I wanted to teach a sidecar course about quantum entanglement. I expected it to be co-sponsored by my advanced lab course and a philosophy course, but I couldn't find any philosophy professors who were interested. Luckily, I found a willing collaborator in the English department, Dave Fisher, who was scheduled to teach technical writing. We created a sidecar course to examine the different ways people write about quantum entanglement. If I hadn't delved into the existing literature to prepare for the sidecar course, I never would have thought to write this book. Aaron Bonning, Michael Weissman, Alyssa Bands, and Tom Bing generously read and commented on a draft of this book. I'm grateful for additional helpful discussions with colleagues, especially Sergei Orazdin, Daniel Weissman, Keith Berland, Vincent Hun, Louise Santos, Ajit Sravastava, and Justin Burton. I take full responsibility, however, for any errors or imprecision. Albert Einstein memorably described quantum entanglement as spooky action at a distance. I recall another memorable Einstein quote, this one from a letter he wrote to the philosopher Eric Gutkind in 1954. There, Einstein explained his view that the scientist's religious feeling takes the form of a rapturous amazement at the harmony of natural law, which reveals an intelligence of such superiority that, compared with it, all the systemic thinking and acting of human beings is an utterly insignificant reflection. In a book about physics, it may be irrelevant to observe that the rapturous harmony of the natural world is increasingly imperiled. And yet, I dedicate this book to the preservation and restoration of the natural world. Introduction. Quantum physics describes the behavior and misbehavior of tiny things, atoms, photons, and electrons, to name a few. What electrons lack in size, they make up for in importance. Electrons are the glue in chemical bonds, so quantum physics is used to understand the chemical bonds that hold together metals, plastics, skin, and every other material. Electrons are the lifeblood of computer chips, for instance, so engineers use quantum physics to design faster, smaller devices. Wherever quantum physics is applied, it's unerringly accurate. The most amazing feature of quantum physics isn't its accuracy or its usefulness, but its brazen defiance of our common sense. Quantum physics challenges our basic understanding of reality itself. And yet, quantum physics started off in a very mundane way, seeking explanations for dry quantitative data. For example, hydrogen gas can emit 4 colors of visible light: violet, blue, aqua, and red. Physicists had carefully measured the wavelengths of these 4 colors: 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers. Surely there's a reason for these 4 specific numbers. But what is the reason? Physicists were scratching their heads. In 1885, a physicist even came up with an equation that fit all 4 wavelengths. But there was no explanation for the equation. It was a purely empirical equation with no theory behind it. Finally, in 1913, Niels Bohr came up with a theory that explained the 4 wavelengths. He claimed that the electron in the hydrogen atom is constrained to have certain amounts of energy. The electron cannot gain or lose energy smoothly. It can only make quantum leaps